So, welcome to today's MAFO Tech Talk. My name is Andy Huthoefer. I'm the Vice President of Marketing and Product Management at Satislow, and I'm excited to talk to you today about film lamination, a truly new and disruptive coding technology. Let me start by saying that in-house coding is a great benefit and asset for any lab. It allows the lab to really control its own destiny in terms of quality and in terms of delivery times. No more sending jobs out to a third-party coding lab and waiting for days to get the lenses back. It also allows the lab to put some additional profits to the bottom line. However, starting an in-house coding lab, especially for a smaller lab, also comes with significant challenges. To begin with, it's a fairly complex process and there's a need for highly skilled staff. It also adds a significant amount of process time, 3 to 10 hours for hard coding and AR coding, if you do it in the conventional way. The cost of entry for installing a hard and AR coding facility is around 500,000 euros, even for an entry-level lab. So that is also certainly a consideration. And on top of that, there are space requirements and the need for a clean room. So we asked ourselves, is there an easier way to get into in-house coding? And we believe the answer is film lamination. Let me tell you about film lamination. It all starts with the Satislow TechFilm AR, which is central to the lamination process. We're essentially taking all of the complexity of hard and AR coding and we're putting it into this film by already prefabricating the film in our manufacturing facility. So as you see on the screen here, the film consists of a carrier foil. On the one side of it, there's an optically clear adhesive that allows it to adhere to the lens. And then on the other side, you actually have the complete coating package with hard coating, multi-layer AR coating, and a super hydrophobic coating. And all that the lab then needs to do is laminate this film consumable to the actual lens, which is a much easier process than going through the full hard and AR coding process in-house, like in a conventional coding lab. In fact, it's a process as easy as 1, 2, 3. You first clean, then you prepare the surface, and then the lab laminates the film onto the lens. Let me go through it one by one. In the first step, the lenses are being cleaned in a tabletop device called the Hydra film. It's a small washing system, and it's absolutely crucial to the success of the process, because like with any coating, film lamination requires a perfectly clean lens surface. Otherwise, if there was still dust or fingerprints or anything else on the lens, all you would do with coating the lens is sealing those imperfections, and the lens would essentially go into the trash. So instead of doing this, we have a nice, simple cleaning process, only takes 2 minutes per pair and is being performed in the Hydra film. From there, the lenses go into a small plasma oven, which is also a tabletop device. The process there takes 4 to 5 minutes, and what's happening in the plasma etch plasma oven is that the surface of the lens is being treated so that later the TechFilm AR adheres perfectly to the lens. And from there, we go to the actual lamination in a device that is called the film pod. In the film pod, there are 2 process stations. The first process station is designed to thermoform tech film AR to the shape of the lens back curve. That's critical because by doing so, we can avoid creating bubbles or wrinkles in the film when we actually laminate it to the lens. And then in the second step, we are doing the actual lamination. So essentially sticking the tech film AR to the lens surface. After that, the lenses are ready for etching immediately afterwards. The process time in the film pod takes 4 to 5 minutes per pair. So let me describe a little bit what the benefits are and why this technology is truly so disruptive and different compared to conventional lens coating. First of all, there's the low cost of entry. The set of equipment that I just showed to you is very affordable, and the investment is about 1/3 of that of a conventional coating lab. And on top of that, also no clean room is needed. Secondly, it is really simple to operate. Staff is able to coat lenses after just a very short training. Any decent operator will very quickly pick up on how to laminate lenses. It also comes with easy installation, and maintenance efforts are quite low. Very important is this point. Film lamination is an ultra-fast process. The lenses are done in 15 minutes per pair total process time. This makes it especially interesting as an express service capability for labs, and they can actually charge a premium for such an express, for lenses that are produced in such an express line. Now, the 15 minutes per pair, that assumes that the lab is starting with frontside AR coated planks and then laminates the tech film AR on the back surface of the lens. This is also how we are launching this technology into the market. But later this year, we will offer the option to laminate front and back side. In that case, the process time would be 30 minutes per pair, which is still a lot faster than the 3 to 10 hours of a conventional hard and AR coating process. Next, I want to point out space savings. This setup is extremely compact. We're talking about 54 square feet or 5 square meters. And there's also no clean room required, as I mentioned earlier when we talked about the investment. So again, it's very easy to integrate such a film lamination lab into any facility or even into an in-store lab for a larger optician or optometrist, for example. And the outcome of this process is actually a very superior lens product. The lenses produced with film lamination are up to 18 times more impact resistant than standard CR39 lenses. And that means, depending on regulations locally, labs are able to grind those lenses up to 40% thinner, and with that also lighter. In addition, the natural physical property of the film means that there are no Newton rings and no Newton rings on the lenses, and that you always get the same reflection color for every lens. The reason that there are no Newton rings is that the film is a little bit thicker than a conventional hard coating, so physically that phenomenon just doesn't occur. On the sustainability side, which is a topic that becomes more and more important, of course, I'd like to mention that there are no hazardous materials in the lab, for example, no hard coating lacquers, and that makes the waste disposal topic much easier for the lab. It also means that the power and water consumption is much lower than with a conventional AR and hard coating lab. We have so far already coated about 300,000 lenses with film lamination. So, we've proven it out very thoroughly at our pilot sites, and the yield at those pilot sites has been 99% or higher for laminated lenses, which is actually the same or better as conventional coating. So in summary, we believe that film lamination really makes it a lot easier for small labs and new lab entrants to get into AR coating. The total capacity or throughput of the system is 25 to 30 lenses an hour, so 200 lenses in an 8-hour shift, which is a great capacity for a startup lab or an in-store lab. And really now makes it easy to bring the entire value chain from surfacing to coating to finishing in-house and eliminate dependencies on external sources for quality and delivery times. And then in addition to that, there's a second attractive use case also for mid-size and larger labs, which is offering the products that come out of a film lamination line as premium products, either based on the properties that I mentioned of high impact resistant, thinner lenses, no Newton rings, or as an express service, which then again allows the labs to charge a premium. As a bit of an outlook, I want to say that film lamination is also a platform for other really interesting features that we will be able to introduce in the future. These tech films could also be used, for example, to laminate polarized films, tinted films, mirrors, and many other properties onto a lens. And with that, it could actually do for coating what freeform has done for surfacing. So I'm really meaning it when I'm saying here on this final slide that the possibilities with film are truly endless. And that brings me to the end of the MAFO Tech Talk. And thank you again for listening to this presentation. And I'll be very happy to answer your questions in the Q&A session. Thank you.
Andy, thank you very much for your interesting and well-prepared and clear lecture about a new and exciting coating technology. Is that really the first time that such a technology has been introduced to the market? I think, for example, when we look at polarizing glasses, we are using such films, and I'm not sure if it has been used also for anti-reflex coatings.
Yeah, thanks, Peter, and thanks for the question. To my knowledge, for anti-reflective coating, a film solution like the one that we are now introducing, where film is being laminated on the back side of the lens and eventually also on the front side, has not been introduced like that. You're right, of course, polarized lenses, they are using polarized films, but that is something that's happening in mass manufacturing. And it's being embedded, I believe, in the molds and casting. But in a lab, I don't think that a film technology has been introduced up to now.
Ah, okay. Mm-hmm. And the tech film is flat, and the back surface commonly not so. So my next question is: are there any restrictions regarding the curvature or the cylinder or the diameter or the blended shape of the back surface?
Yeah, that's also an excellent question. And yes, you are correct. The tech film is indeed flat when the lab receives it. And part of the lamination process then is to pre-shape the film to the curvature of the lens. That is happening in a step called thermal forming with moderate heat temperature in the range of 40 degrees Celsius. sorry, 100 degrees Celsius, and with moderate vacuum. But indeed, there are limits to how much you can bend the tech film, and the curvature depends. We express the curvature in a diopter value, and so it depends on the index of the lens material. So, for example, on a 1.5 CR39 lens, the maximum curvature is about a 8 diopter curve. On a 174 material, that equates to about 11.5 diopters. That means you can cover a very broad range of prescriptions. It does mean, though, if you have very high base curves, for example, for like wraparound sports classes, that is indeed a limitation. Certainly something we will keep on improving and trying to push the limits further. But at the moment, those diopter values is what we can cover.
So that means for a normal single vision with a high index, a -10 lens is possible. And for sport lenses, it's also very difficult to make them optically with a 7 base curve for -5 or so is normally very difficult to wear these lenses. And what about etching or drilling the lens? Are there any restrictions?
Yeah, etching, a normal V-bevel or a flat bevel or a grooved lens for nylar frames, that is all not a problem. We do have etching recommendations. Ideal are dry etchers, but it is also possible to etch with wet etchers if you follow the etching recommendations. Drilling is still a bit of a challenge that we're looking into. It's not so much the drilling process itself, it's more the mounting. And there's a chance that you damage the film. So at the moment, we're not recommending the technology for drill mounts, but all regularly beveled lenses, with the exception of drill mounts, are manageable very well.
Yeah. Okay. And I have seen in your lecture that the shape of the tech film is kind of rectangular with round edges. Yes. Does this mean that you may see the transition from the tech film to the naked lens if the frame is very large, or do you have different shapes or sizes?
Yes, we do have 2 different sizes, and the larger size, obviously, for the larger frames, but also yes, there are limitations. I mean, if you had an extremely large frame with a unfortunate shape, there could be a situation where it doesn't cut out. In that case, we would not recommend to use that technology for that frame. The larger frame is 65 millimeters by 45 millimeters for the active film disc size. So it is quite a large surface, but if you went beyond that, yeah, we would not recommend this, because you would not want to have that border between the film and no film visible on the lens. The reason, by the way, that the shape is this more oval or rounded rectangular as opposed to simply a circle is to improve again the how the film conforms to the shape of the lens and to avoid wrinkles and bubbles. So if you have a completely round surface, and you try to push that against the lens, there's a bigger issue with wrinkles and bubbles than if you go with this, rounded rectangular shape. That's just something that we found out, in many tests and trials to make sure we do avoid wrinkles and bubbles, and that's how this shape originated.
Mm-hmm. Ah, interesting. And can you give us some numbers on the, or some more details on the color and the intensity of the residual reflex, and maybe of the contact angle of the hydrophobic layer, so that it's easier for us to compare it with a, I say, standard coating?
Yeah, no, sorry, I don't have any numbers that I can give you right now, but I can tell you it is a super hydrophobic coating, so it has a comparable contact angle to our other super hydrophobic
it's in the same range.
It's in that same range. The color is a typical green AR coating reflective color. So as you see it on many frames, like, the one that I'm wearing has a green AR. It's actually not laminated. I got laminated on my other frames here, and you can't see it here in the camera, but when I look at them and compare them, they have basically the same greenish color hue. So again, a very typical color for AR coating. And as far as the transmission, again, it's a typical AR. I mean, we basically shaped it to match our regular AR coding process, also for the reason that in the initial launch phase, we are laminating only the back surface of the lens. So obviously we want to make sure it matches with the front surface of the lens, which is produced in a conventional AR coating. So we match the color, we match the transmission, etc. So it all fits together.
Yeah, that was the background of my question. When the wearer looks at the spectacle and the front surface looks much different than the back surface, it would not be so nice.
Yeah,
but
exactly.
Okay, you
so
matched.
Yeah, it's matching.
Mm-hmm. And what is you said that there are two things I'm wondering about. One, you say the thickness can be reduced by 40%. Okay, one thing. The other thing is the layer is thick enough so that no interferences will occur with normal sunlight. So that means it's much thicker than the coherence length of normal sunlight. But how thick is it?
Yeah, so I can tell you that it's a 1/4 of a millimeter. So
a 1/4 of a millimeter.
250 micrometers, roughly. So that is not a lot of thickness. When you look at the total thickness of a lens, a 1/4 of a millimeter is 0.25 is quite little. But what it does do is it increases significantly the impact resistance of the lens. It's similar to, I guess, car windows, where you have a foil, in the window. So if there's an impact, right? I mean, something wouldn't come through the car window. It's similar here, which actually we even found it doesn't even crack. So the stabilizing properties of this film really prevents the lens from cracking, let alone from puncturing it in the typical drop hole testing. And so we did drop hole testing. We also did some testing with projectiles that we were shooting at the lenses. And it is very, very difficult to break these lenses because of that film. And that's why we say that, at least in theory, it is okay to surface them, to grind them thinner from the perspective of the impact resistance. Now, of course, you still need to follow whatever the local regulations are. There may be legal restrictions, right? How thin you are allowed to surface a lens, and of course you have to follow that. But in our testing, we have just seen that the impact resistance is actually 18 times higher once the lens is laminated, and with that, the risk of a lens breaking is much lower, and therefore you could surface it thinner. But yes, you do add this 0.25 millimeter of film thickness to the lens.
Mm-hmm. Yeah. Okay. So it's a quarter of a millimeter, and I was wondering where about this 40% number, because, for example, you have a plus lens and the minimum thickness is at the edge, and there you have a simple geometrical restriction, maybe 0.7 millimeters or so. So what you can do is you can reduce it to 0.5, and then you add the layer, so you are again at 0.7, and the center thickness is pretty much the same. And with minus lenses, maybe you can go from 1.5 millimeters in the center to 1 millimeter or something like that, and without violating or without lowering,
risking that your lens will break. Yeah, exactly. It's really more for minus lenses. You're right. On plus lenses, you are tied by the necessary curves for the optics. You can't really go lower, in the center thickness than what you need to generate the dioptric power, right? So yes, you're right. There it wouldn't apply, because there is no that would require for the film to add optical power to the lens, which it does not. The film is optically neutral, right? So the plus lens is not going to be stronger or weaker, and you wouldn't want that either once you put the film on it. The film has no impact on the optical power of the lens. By the way, it's also perfectly suitable to laminate this film onto an aspheric surface or a progressive surface. So no problem with that at all. What you can't laminate it over is over a bifocal plastic or organic lens, because those lenses have the step in, because you have the different curvature of
discontinuity.
Yeah, exactly. And so, you couldn't laminate over that step. That wouldn't work. So that is a limitation. So I should have mentioned that when you asked about limitations earlier. So it's not a suitable technologies for bifocals or trifocals.
And you mentioned that it's optically neutral. When I was thinking about your lecture, my idea was it cannot be if it's so thick and the rays like a window, the glass of a window which has parallel sides, but what if the rays are refracted in or oblique rays passing through this layer? There must be maybe a very small modification of the light bundle, but you haven't found any significant deviations in power or something like that.
No. It's yes, it is thick enough so you don't have any interference fringes, but it is not thick enough that any impact on the light rays would be noticeable in a measuring instrument that is typically being used in our industry, or even less so by the human eye. So no, there's no measurable impact on the dioptrical power.
Mm-hmm. And one more question regarding the durability. You say the impact resistance, but what about scratch resistance, for example?
That's a good question.
Do you have
too.
Numbers on that? Or
actually, I do. Yeah, we did. We just got our results back for real life simulation tests from Colt's laboratory here in the US, and the value for the real life simulation was 4.08. Now that may not mean much to the viewers, but to put it in perspective, that is a good mid-range for a scratch resistance. So we are not claiming that the scratch resistance is the highest in the marketplace. There certainly are coatings that exceed that. If you look at something like a Crisal Rock or something like that, that really optimizes for maximum scratch resistance, that would be higher. But it is a good mid-range. You may have seen these charts from Colts Laboratories where they give you a benchmark of where your lens lies, and we are kind of at the top of that bell curve. So that's where we lie there. So a very nice scratch resistant, fully sufficient for everyday life. The other advantage that the technology has is a very high thermal resistance. So we have tested that also. And for example, put the lenses on a hot roof, on a tin roof in the summer, and just let them sit there, some of those laminated lenses alongside with some conventionally coated lenses. And we observed that the conventionally coated lenses showed crazing, whereas the laminated lenses did not. So there is, because of the more elastic properties of that coating, it kind of can flex more with the temperature differences. And so that means that a laminated coating, let's say you place it on your dashboard in your car in the summer, which of course you shouldn't do with your coated
but we do.
But it happens, right? And so those lenses are much more forgiving in a situation like that.
Okay. And I have one last question. As far as I understand, you can, or the lab can produce more or less 25 lenses per hour with such a small unit, but the times are a bit different. So in the first step you need only 2 minutes, and then you need 4 to 5 minutes. And you say the lab does not need a real clean room, but if the times are so different, so some lenses will have to wait for the next step, and when they are waiting and they have been cleaned, they can get dirty again. So what is maybe not, you don't need a clean room like you need for the standard coating, but I need at least some restrictions are there for the.
Yeah, no, I understand your question. So a couple of comments. I mean, first of all, I guess the process time is about 2 to 3 minutes per station. The 4 to 5 minutes, that is in the film pot, in the actual laminating machine. But within the film pot, you have again 2 stations. So there's the thermoforming station and the actual lamination or stamping station. And each one of those is 2 to 3 minutes. So you end up with 4 to 5 minutes in the end. So you kind of have this, I guess in German, the word would be the takt time or Taktzeit, where you go, you have 2 minutes in the cleaning, 2 minutes in the plasma etching, and then 2 minutes in the thermoforming station, 2 minutes in the stamping station for the actual lamination in the end. So there's kind of a consistent flow, which also explains why you get to 25 lenses an hour, even though the last machine takes in total 4 to 5 minutes. Right? So I wanted to clarify that. Nevertheless, I mean, you are of course right that there will be situations where a lens is sitting in its tray waiting for the next step. That can happen just because the next step isn't ready yet. It can also happen because the operator walks away and, I don't know, takes a sip of water or eats a sandwich and then comes back, right? So that is absolutely a valid point. So, and yes, we do have an extra step before the actual lamination. There is a air shower in the film pot. So in that machine itself, there is a little device on the side of the last station in the film pot, and you push a button, and then ionized air comes out of a nozzle, and you hold the lens under that nozzle, and that kind of blows off any dust that may have gotten onto the lens while the lens was waiting after the cleaning step.
Okay.
We do account for that.
Maybe I've missed that point in the lecture. Okay, Andy, thank you very much for answering my questions. That was very interesting, and I wish you that the product will have a great success. Thank you.
Thank you very much, Peter. Thank you.